Hi, good morning, everyone. I hope you are all doing well. First, let me start by saying just few words about my background. I am a student of Bangladesh University of Textile uh, in Bangladesh. On behalf of our team, I will give you details idea about our work. As you can see on the screen, our topic is alternative way of lead-based ionization radiation shielding property, epoxy-based composite design for functional textile for the application of ionization radiation shielding. Here, my name is Bilal Uddin Rabbi. I am here to present the topic. As you can see on the screen, I have decided my presentation in two main six part. One is introduction, then second is hypothesis, then methodology, then result analysis, then application, conclusion, and last acknowledgement. First, I would like to give an overview about our research and why it is important to go further research. Our research is about an epoxy-based composite design as an alternative to lead in shielding from ionization radiation. Gamma and X-ray radiation are used in industry, medical diagnostic center, nuclear research facility, radioisotope research, and nuclear weapon development. And for this reason, radiation shielding is essential for radiation emitting equipment user to reduce or mitigate radiation damage, because radiation shielding deplete radiation by inserting a shield of absorbing material between any radioactive source. And for that reason, we use lead. One question has come in our mind: why we use lead? Because lead is the most widely used shielding material. Its ability to shield X-ray efficiently is superior to that of other material, owing to its high Z number, high density, and low cost. But lead-based shielding material often have a few significant downsides. For example, it has high toxicity, weight, poor flexibility, and poor chemical stability. For this reason, we want to uh, another reason that they have a blind absorption zone for X-ray in the 70 to 90 kilovolt range is more significant. Polymer composite with high atomic number filler can replace toxic lead in ionizing radiation shielding application. That's why we design an epoxy-based composite as an alternative to lead. Then one question have come all of your mind: why we choose if epoxy resin based composite? I will tell you why. Because epoxy is a non-toxic, lightweight, flexible, and inexpensive radiation shielding material to replace lead. A hybrid composite of bismuth and tungsten nanoparticle can block high and low waves. So we used a tungsten nanoparticle as a reinforcing material in epoxy resin. Pure tungsten offer more excellent attenuation qualities and a thinner half-value layer than traditional shielding material. Let's now look at the next slide, uh, which shows about our literature review. Developing an epoxy-based composite. Uh, we use nanoparticle for reinforcing purposes with different layer of nanoparticle can be used to develop a fabric with an epoxy-based composite. Fabric can be used for the outer layer and inner layer, and an epoxy-based composite can be used for the middle layer. The toxicity of lead and epoxy-based composite are being measured and compared. Uh, we want to determine the potential exposure to lead for medical purposes. Uh, to develop a fabric that absorbs electromagnetic noises. Let's now look at the next slide, which shows the methodology. At first, we know about material and chemical needed in our experiment. For example, at first we prepare pure epoxy resin, and for this we need three chemicals. One is epoxy resin 128, which is bisphenol A epichlorohydrin based liquid epoxy resin 128 counter type of DER 331821 and NPEL 128. Our second chemical is isophorone and third is Teflon mold. For preparing a composite, we need six chemicals. First one is diphenyl ether, then second one is oleic acid, third one is trioctyl phosphine oxide, which is known as topo, and fourth one is tungsten hexacarbonyl and ethanol, and last one is high purity argon gas. All of this chemical we used for making composite and pure epoxy preparation. Then go to the next slide, and which is the method we used in preparation of composite and epoxy resin. For a preparation of matrix, at first we know preparation of matrix. We divided into 5 parts. First one is mixing, second one is mechanically stirring, third one is mixing, fourth one is magnetically stirring, fifth one is finishing pouring. Mixing 2:1 ratio. Liquid bisphenol A epichlorohydrin epoxy resin and isophorone diamine. Then second one is mechanically stirring for 5 minutes. We use grinding reinforcing particle. Third one step is mixing the powder and the resin and with hardener mixture. Fourth one is magnetically stirring for 15 minutes, keeping the mixture in the ultrasound bath for 15 minutes. Finishing pouring in the Teflon mold, drying at a room temperature for 24 hours. Then we prepare material step by step. We use solvothermal decomposition of tungsten hexacarbonyl as a route to tungsten nanoparticle synthesis. At first, adding 6 millimole oleic acid topo with 30 millimole diphenyl ether in antique distillation flux. Then we inject high purity argon gas for 8 minutes, then preheating the mixture at 130 degrees Celsius for 5 minutes. Then our third step, we added 2 millimole tungsten hexacarbonyl. Then in fourth step, reflexing the mixture for 15 to 60 minutes. Fifth step, forming the nanoparticle of tungsten. As a result, we add 60 millimole ethanol to precipitate the tungsten nanoparticle. Then separating the tungsten nanoparticle from the solution, we need velocity 6000 RPM for 10 hours. Then finally redispersing in hexane. Then we prepare composite. We divided this process into 5 steps. One is preparation, then second one is mixing, third one is hardening, fourth one is bathing, and fifth one is drying. In preparation, we grinding the reinforcing particle for 15 minutes. In mixing, added liquid epoxy, stirred 15 minutes with magnetic stirrer. Our third step is hardening. We added hardener into 2:1 ratio. Ultrasonic water bath sonication 40 kilohertz for 1 hour. Then in our fourth step, as we call it bathing, we mechanically mixed for 5 minutes, then placed ultrasound bath for 10 minutes. Our last step is drying. We pour into the mold, dry at room temperature for 24 hours. As a result, the composite will be prepared. Then go to the next slide. The next slide is result discussion. To improve the shielding property of a composite, tungsten filler should be added as much as possible. However, with the tungsten content reaching 85% weight percentage, the mechanical property of the composite decrease significantly as the resin cannot fully impregnate the filler. So, tungsten epoxy composite were prepared with 4 different weight percentages: 30%, 50%, 70, and 80%. The test result from a transmission a measurement in different thickness of WEP80 sample. The HVL of epoxy 80% is much lower than that of a heavy concrete, one of nuclear power plant most common shielding material. Even though the HVL of WEP80 is higher than that of lead, it is still a suitable shielding material because it is light, not very dangerous, easy to make, block neutron radiation very well. In comparative study between tungsten oxide and bismuth oxide nanoparticle, it is found that the higher Mach value were reported for the tungsten oxide reinforcing nanocomposite, which can be deduced that epoxy tungsten nanocomposite showed better radiation attenuation performance for comparatively lower electrovolt like 81 kilo electrovolt. Due to the lower kh discontinuity energy of tungsten and bismuth, tungsten oxide show a lower MEFP value than bismuth oxide, which is significant at the lower energy level. In nuclear medicine, a low energy level is maintained. So it is suitable for the nuclear medicine sector and radiation imaging machine such as Röntgen, mammography, or PET scan. Here we see the machine picture we used in our experiment. First one is a FISM index, which is known as field emission scanning electronic microscopy with energy dispersed X-ray spectroscopy. We used these to study and analyze the elemental composition of tungsten carbide. The second machine we used is a manual hydraulic press machine. We used it to form a different disc thickness of tungsten carbide sample. Then in third figure we see tungsten carbide powder is placed on a evaluable pellet die to form a disc shape. Here you can see evacuable pellet die and tungsten carbide. In fourth picture, we can see the 1 centimeter thickness of tungsten carbide discs and right lead discs. The fourth picture, we can see 1 centimeter thickness of tungsten carbide discs in right and lead discs. Here you can see sample, then lead block, sodium iodide detector, and radioactive source. Result. Our next slide is result discussion. You can see X-ray transmission measurement system geometry. Here we use here dosimeter, ionization chamber. Then we can put shielding material here, lead and lead here. Experimental condition under different reaction time. Experiment 1, we use tungsten hexacarbonyl as 2 millimole, oleic acid as 6 millimole, trioctyl phosphine oxide as 6 millimole, and here the reflux time will be 15. Average particle size from sex is 15 and standard deviation in particle size zero point 0.2 nanometer. One thing we have to understand what is SAX means. SAX is small angle X-ray scattering. We used it to quantify nanoparticle density of different samples. In second experiment, we used tungsten hexacarbonyl as 2 millimole, oleic acid as 6 millimole, trioctyl phosphane oxide as 6 millimole. Reflux time will be 30. And here, the average particle size will be 25, and standard deviation in particle size will be 0.3. In third experiment, we use tungsten hexacarbonyl as 2 millimole, oleic acid as 6 millimole, trioctyl phosphine oxide as 6 millimole. Reflux time will be 60 and average particle size will be 28 and standard deviation in particle size will be 0.3. In table 2, we can see reaction condition with varying surfactant concentration. And here, average particle size will be 45 nanometer, 25 nanometer, and 30 nanometer. And a standard deviation in particle size will be 1.4, then 0.3, and 0.4. And the reflux time we get 15, 30, and 60 minutes. In our next slide, we discuss about the application. More radiation gadgets are in our life as scientific technology advances. Lead and iron are conventional radiation protective substance in epoxy composite, but excessive particular gravity tungsten filler shield are the quality choice. Radiation protection, nuclear medical, and NDT. NDT stands for non-destructive testing. It refers to an array of inspection that allow inspector to evaluate, collect data about a material, system, and component without permanently altering it. Our second is isotope vial and container. Third uses it will be custom shielding component, calorimeter for X-ray detector, multi-leaf calorimeter, and radiation imaging machinery. Conclusion. The experiment results show that the amount of tungsten nanoparticle in the epoxy matrix increase the radiation shielding property. But on the other side, mechanical property of the matrix decrease respectively. More minor tungsten result in better shielding. Higher energy energized gamma radiation result in undesirable degradation of the polymer chain, an essential factor for using the composite in nuclear power plant. Tungsten is less suitable than lead and bismuth if we consider only radiation property. Uh, lead is tungsten epoxy is lead toxic, which suit the medical field. Working with different polymer with higher Z will open the door for effective, cheaper, and duration of shielding material. In conclusion, I would like to thank Nigar Nahid and Faisal Ahmed Ridoy for their cordial support and contribution to this work. They are undergraduate student of wet processing engineering at Bangladesh University of Textile. That's all. Thank you very much to have patience to hear about my work. I hope you are all doing well. Thank you very much.